Now that I just posted a video on how to solve easier circuits, I'm going to give you a video that talks about how to solve harder circuits. And in these circuits, basically what you would have is more than one battery and more than one loop. So how will we solve this particular circuit here? It's going to rely on Kirchoff's laws that we talked about earlier in class. And basically there's a loop rule and there's a junction rule. Let me explain. So here we're going to talk about the different loops within this particular circuit. So you can imagine here up top, we've got one loop, which is one enclosed space based on these resistors and the battery and the wires. Down here, we've got another loop like this, which is another enclosed space that we can have. So what Kirchoff is basically saying is that if you go around a particular loop, the sum of the voltages should equal 0. There's another law that he has, which has to do with the currents and the junctions. So if I were to take a look at the circuit and cut it right here and right here, what I would get is 3 wires, sort of like this one here, and this one here. And in those 3 wires, because they're not looped, but they're single pathways, I can have 3 separate currents. Let's call the first one up top I1. Let's call the second one down below I2. And let's call the third one I3. You can pick them to go in any direction you want. It really doesn't matter. If you are consistent with solving everything, then what will happen is at the end, you'll either get a positive value for your current, in which case you guess the right direction, or you'll get a negative value, in which case you guess the wrong direction, but that's okay. The math will tell you it goes the other way. So let's go ahead with this. I'm just imagining that the currents go in these directions as I've indicated here, but I could be wrong. Let's find out. So what we're going to do is write the loop equation for this upper loop here. And typically what you want to do is start at the back end of the battery where the voltage is 0 and then go up in voltage as you cross the battery. So we'll go up 5 volts here as we cross that battery. So up 5 volts. Then you're going to take I1 across the 1 ohm resistor. So as I1 goes across the 1 ohm resistor, what's going to happen here is you're going to drop voltage. So minus I1 times 1 ohm. And then you're going to come around here, and now you've got a different current here. Remember, this is this branch that carries I3. So now you're going against the direction of current I3. So you're not exactly dropping I3 times 2. You have to go up I3 times 2. You got to change the sign because it's pointing in the opposite direction. So plus I3 times 2. And then you come to the back end of the battery, which is where you started from. Okay? So this is a valid equation for the first loop, the upper loop right there. For the second loop, I'm going to start at the back end of the battery. I'm going to traverse the battery, and I'll gain 10 volts. So 10 volts by going through that battery. Then I2 goes across 3 ohms. So that'll be a drop of I2 times 3 ohms. And then we go up here, and we traverse this battery, but backwards. We're starting out at the high end of the plate, which is 5 volts, and going to the low end of the plate here, which is 0 volts. So I've dropped 5 volts there. That's indicated by minus 5 volts. And then I traverse this resistor, 2 ohms, in the direction of I3, and it should be a drop, I3 minus I3 times 2. So that's a complete equation for the second loop. Now, if we want to zoom in and take a look at the junction rule, here are the 3 currents, as we described earlier. You can just pick a junction where all 3 of them show up. So let's just say in this spot right here. All right, I could have just as easily picked this one over here. It doesn't really matter. But now what we want to do is talk about everything that flows into this junction as a positive current and everything that leaves this junction as a negative current. So flowing in is I1 and I3, but leaving is I2. And you can think of this as kind of like, your job gives you money, your parents give you money, and then you blow it on rent and food and things like that, okay? So it's basically a statement of conservation of mass. Everything that flows in must equal everything that flows out. The number of electrons can't be created or destroyed. So that's the junction equation. So now we've got 3 equations, loop 1, loop 2, and the junction equation, and 3 unknowns, I1, I2, and I3, like that. So we should be able to solve this. However, it's not that easy all the time. And so what happens is you have to fiddle around with this. There are systematic ways to do this using linear algebra, but I am not allowed to use that, so I'm teaching you with one hand tied around my back. So I'm going to show you a combination of things like substitution and multiplication and adding equations together that should work. So let's take a look at it. Here I've copied the loop equations over on the next page. So this is loop 1 and this is loop 2. One of the very first things you can do in any of these equations is see if you can simplify them. So one way to do that is see if there's similar terms. Here's a 10 volt and here's a 5 volt. I combine positive 10 volts with minus 5 volts, I get plus 5 volts. This term I just bring down, this term I just bring down and copy it, okay? So now I've got this equation here, that's from loop 2, and this equation up here, that's from loop 1. I can just eyeball it and look. If I add these guys together, am I gonna get anything canceling? Well, I could cancel the I3 times 2 ohms and the I3 times 2 ohms, but I'm gonna be left with an I2 term and an I1 term. So I'm still gonna have two variables. It's not like I can eliminate one variable totally. So I'm gonna resort to something here. I'm gonna use the junction equation and basically sub in, instead of I2, I'm gonna sub in I1 plus I3. So if I can go into one of these equations and basically sub in for I2 and put it in terms of I1 and I3, then maybe I would have another equation that has I1 and I3 in it. So then if I have two equations with two of the same unknown variables, I might be able to somehow cause them to add together in ways that will cancel one of them. Okay, so I'm going to plug in I1 plus I3 for I2 into this equation here. All right, so let's do that. This equation comes down, follow the line here, all right? And what we have here is 5 volts minus what used to be I2 times 3 ohms. And instead of I2, I'm plugging in I1 plus I3 minus I3 times 2 ohms. I expand this out. I distribute the 3 ohms over these two parts here. And so I get 5 volts minus I1 times 3 ohms minus I3 times 3 ohms. And then this term here is just carried down there. Now what I see is that I have two I3 terms. I've got an I3 times 3 ohms and an I3 times 2 ohms. I can combine them and get an I3 times 5 ohms, right? So that's fine. So now I have this equation here, 5 volts plus minus I1 times 3 ohms minus I3 times 5 equals 0. And the equation from loop 1 is somewhat similar, plus 5 volts minus I1 times 1 ohm and plus I3 times 2 ohms. Is there some way that I could basically add these guys together, these two equations here, such that I could cancel one of these terms? Well, let's see. So if I go over here and take a look at this up at the top, here's one of the equations and here's the other one. And what I notice is that I could cancel things if I was able to basically have this guy be slightly different. I want this to be positive down here, and I'd also like it to have a 3 there and not a 1. So what if I multiply it by minus 3? I multiply this whole equation here by minus 3, and I have to multiply the other side of the equation by minus 3 also, but minus 3 times 0 is still going to be 0. So if I multiply every term here by minus 3, that's a perfectly reasonable operation, and what I'm going to get is the following. Minus 3 times 5 volts is going to be minus 15 volts. Minus 3 times minus I1 times 1 ohm is going to be plus I1 times 3 ohms, okay? And then minus 3 times I3 times 2 ohms here is going to give me minus I3 times 6 ohms, because 3 times 2 is 6. So now I have an equation that has this term here that looks like it's going to be able to cancel this term here. It's obvious, it's going to. So I basically add these equations together, and I get plus 5 volts, minus 15 volts, I get minus 10 volts. These terms cancel, as we just said. And this term does add with this term, okay? And what I get is minus I3 times 5 plus 6, which is 11, like that. So now I've got one variable, it's just I3, in this simple equation here. Whoops, go back. And what I can do is basically crank that through and solve it, and I get minus 0.909 amps. That's what I3 is, according to this manipulation of equations. Now, if I have I3, I can plug it back in to get I1. Right? So this equation, for example, here has I3 and I1. If I know what I3 is, I should be able to get I1. So I can do that. I can plug it in. So 5 volts minus I1 times 3 ohms minus I3 times 5 ohms. And so that was just this equation right up here. I just plugged it in. So if I do that, I can multiply these guys out. This ends up being 4.55 volts. This guy, leave it as I1, minus I1 times 3, and I got to combine the 4.55 volts with the 5 volts. I get 9.55 volts minus I1 times 3 ohms. I can grind that down and solve it. I say that I1 looks like it's 3.18 amps. Now, if I've got those, I should be able to go back and use the junction rule. Remember, we said that I1 plus I3 is going to give us I2. So I put these guys together, 3.18 minus 0.909, and this says that 2.27 amps should equal I2. All right, that all sounds good, and you might want to just go on to the next problem in the exam, but you should check it. You should check it by plugging into the loop equations. So what we're going to do is just plug in over here. All right, so this is the loop 1 equation that we had, and this is the loop 2 equation. So in loop 1, we're going to do this. We're going to plug in the amps that we've got. So I1 goes right here, and I3 goes right here. And if you plug those things in and multiply it all out, it actually works. And now I can plug in the currents into this, the loop 2 equation, and I plug it in here. So this ends up being I2, and this ends up being I3. I plug those guys in, and again, it works. So that's reassuring. It indicates that you've probably got it correct. So I'm sorry I can't give you any systematic way for solving these types of more complex circuits, but what I did in this problem illustrates the different types of tricks that you can use. It's just kind of like a combination lock. You got to try one thing, then another, until you finally get it. And definitely don't spend all your time on a problem like this if you've got 22 problems on the exam. This is the one that you should save for last, and if you get it, hey, that's awesome. If you don't, well, you tried hard. Hopefully this was helpful.